Yes, it looks fantastic.
Thank you so much for the introduction, and thank you so much, guys, for inviting me. I have been waiting for this moment. I'm preparing for this moment for a while. What I'm going to present today is part of the paper that we just submitted to Cytometry Part A, actually, for the spectral issue that should be coming at the end of the year or beginning of next year. And the topics are essentially autofluorescing and the impact on signal resolution. But I'm using an example that we are all aware of, the ranking of fluorochromes that we use to define in instruments as a tool for panel design. The other thing is that I will very briefly show you how autofluorescence can be, the effect of autofluorescing on measurement precision and resolution can be understood from the point of view of the cytometry theory, the theories that explain, for instance, the quantum efficiency and background factors and how they essentially impact on the resolution of dim signals. I will be covering effects of autofluorescence extraction, what happens when you do a mixing and you do autofluorescence extraction on resolution. And I'm treating them separately because they independently can have effects on the resolution of signals. And I will be covering a little bit the immunophenotype discovery project that I first mentioned in March when I did the seminar with Cytek. It's the case of the tomato reporter trying to assess the expression of this tomato reporter in different tissues, and including lung. And of course, the effect of autofluorescence extraction on the resolution of tomato in this model. Now, the previous lecture, you can find it in Cytek website. This is not a repetition of that lecture. There are things in that lecture that I had to exclude for the sake of time. And in the meantime, I expanded with further studies and data. So what I'm presenting you today is a different thing, and it's more like what's the theory behind the need of autofluorescence extraction, and why autofluorescence is so pernicious, and we need to all be aware of it because it will affect the consistency in our measurements big time. So when we got the Aurora, the first thing that caught my attention was the three main features that I saw in the instrument. The idea that the instrument could be a sensitive instrument because of the design and the APDs and laser power and things like that. So we were hoping that the instrument was sensitive, as sensitive as, for instance, a Forteza. But two other things that were interesting for us to try and assess was the idea of spectral mixing as a method that will reduce overall spreading in panels. So that's something that we wanted to test. And the other component of the features of the Aurora was the idea of autofluorescence extraction. Now, I need to tell you that when I got the Aurora for the first time, I never thought of autofluorescence much. Most of the samples that I've dealt with have been lymphocytes and things like that. The idea that you could remove autofluorescence was alien to me. And the idea that autofluorescence could be removed via unmixing was also alien to me. So this is something that have been growing on me, listening to lectures on that. And today I want to show you how all these ideas come together, the idea of brightness and resolution, the idea of autofluorescence extraction, how all these components together enhance the quality of your data, and why autofluorescence need to be removed anyway. But when we started doing the study, the first thing we did was a kind of benchmark comparison. We wanted to compare the Auroras with the Fortezas and Cytoflexes and other instruments that we have in the platform. We have around 30 instruments and growing. And one of the things that I wanted to know is, well, where Aurora sit in terms of performance? What kind of application can I use it best for? And the idea of fluor brightness was not only the idea to establish the ranking of dyes to design essentially panel design properly, but also be a fluor brightness to get an idea of sensitivity. Because if you imagine you're running CD4 stain P stain CD4 cells, yeah, in different instruments, and your resolution, your stain indexes are different, you can of course assume that the instrument have different sensitivity. So that was the idea behind this ranking comparison. And for that we used the BD Horizon Human CD4 evaluation kit because it has so many dyes that are really useful and people love to incorporate in the panels. And it gives you also a broad spectrum of excitation and emission. And to assess the brightness of these antibodies and these fluorochromes, we use initially immunotrol. Immunotrol is a stabilized human blood suspension from Berman culture. That was really handy because we didn't have to handle human samples. We will essentially buy a prep that was mimicking human blood and use it for the brightness ranking. And also we use fresh human blood. And actually the choice of the sample made a huge impact in the results. And that's what essentially started the whole project, the whole inquiry on autofluorescing effects. So this is the first result that I want to show you. What you're seeing here is a stain index for CD4 and different fluorochromes. I'm using the Cytoflex, the detector configuration, the Cytoflex LX. In the red line, what you see is the Cytoflex stain index for CD4 and how beautifully bright it is, specifically in regions like B, FITC, and how high it is compared to the values that I was getting with the Aurora. So this is Cytoflex and Aurora using fresh human blood. Yeah. So these results were expected because we already knew that Cytoflex was extremely sensitive. So this essentially fell into what we were expecting to have as a result. But when we compare the stain index with fixed cells, the immunotrol cells, we saw something really interesting, that was a dramatic decrease in the stain index in Cytoflex compared to the fresh blood samples and data. I mean, the stain index that you get with immunotrol are below what you get in the Aurora. And essentially you can see the significance in the differences, that is a massive drop in resolution. In the Aurora, when you compare fresh and fixed, so I will be referring to immunotrol as fixed because it's a very long name. So immunotrol will be fixed and fresh will be fresh human blood. You see the same difference. So fresh is always brighter, or fluorochromes with the fresh samples are always brighter than when you assess them with a fixed sample. And the funny thing is that not only there was a decrease in intensity, but there was also a rearranging of the ranking, which is very curious. So if you see here in the top, I have the fresh ranking for all the fluorochromes in the Cytoflex. Can you see my laser pointer? No, because I don't have the laser pointer. Now, laser pointer. So can you hear? Yes, okay.
Yes, we can see it. Thank you.
Okay, perfect. In the top one, you have the fresh human blood in Cytoflex, and all the dyes essentially rank and order with a heat map, but also showing you the stain index that we score. And this is what you see when you have the fixed samples, and you see that many dyes change the order. So if you take out of the analysis the Percy Psi 5.5 by FITC that are one of the dimmest fluorochromes you have in the assessment, and P and Psi 5, most of them will switch positions. They will do that in Cytoflex. They will also do that in the Aurora. Now, when you look carefully at which dyes are changing and in which direction they are changing, you notice that dyes like Brilliant Violet 480, Brilliant Violet 510 tend to decrease their stain index, while dyes like APCR 700 tend to increase the relative brightness. So you get essentially an increase in the relative brightness of dyes that are in the red regions, and a decrease in the relative brightness of dyes that are in the violet-green regions. And we compared the autofluorescent levels of both the immunotrol and fresh blood cells, and we found that there were massive differences. So there were massive differences both in terms of intensity levels, so MFIs across all detectors of Cytoflex. This is immunotrol. The black ones here are the fresh blood cells. And you also see a difference in ratio of intensities. There is also difference in terms of normalized spectra. So if you tend to normalize the spectra of these two unstained samples, you see that immunotrol will peak around the violet 525-40, while the fresh blood cell will be peaking around the UV region in the same kind of detector, the same green region. And in the Aurora, you get a beautiful picture. I mean, in Cytoflex, you have 20-something detectors, and the Aurora has 64. When you look at all the detectors in the Aurora, you get a beautiful picture of the whole detail of the spectra signature between immunotrol and fresh blood cells, and confirming the ratio being higher in the violet region. and the difference that are mostly in the yellow, green, and the green regions of the violet, the UV, the violet, and the blue. Now, something that was really interesting was that since I was looking at these changes in stain index that were somehow related to the intensity levels of the immunotrol and the ratio with the human blood. What I did here was I ratio the MFI of the unstained samples between immunotrol and fresh blood. So this is what the ratio AF means. And here I'm also showing you the ratio of stain index, so how much the stain index in the fixed samples are compared to the fresh as a ratio. And what you can see is a beautiful opposite kind of an inverse correlation between the increase in autofluorescence and the decrease in stain index ratio, and so on. You see that in every single path. Whenever the autofluorescence goes down, then the ratio will be closer to 1. Which tells you something like this, essentially stain index and the ratio between stain index is inversely correlated to the ratio of autofluorescence. And the brightness that we know and the brightness that we use, in a way, based on these results, will be a function of the autofluorescence of the carrier, which is very important when you're thinking of designing a panel based on rankings done in CD4 cells, but you try to use this ranking to study myeloid cells and cells that have high autofluorescence. Now, another thing that happened that goes into the same direction of the inverse correlation between stain index and autofluorescence is what happened with dyes like PerCP Psi 5.5 and Brilliant Blue 700 in the Cytoflex. And what I'm showing you in the black line is that how they look like in terms of normalized stain index for fresh cells and how they look like in terms of normalized stain index for immunotrol. And something interesting that happened with PerCP and Brilliant Blue 700 is that instead of peaking where they should, which is the blue 690, 50 in the Cytoflex, they essentially start peaking in the red region, in the red 712, 25, the Alexis Fluor 700 detector, yeah? And it happens in both. And it happens specifically, not only in these dyes, but any other dye that have a complex emission pattern in which you can see the emission and the stain index and the resolution as a function of changes in autofluorescence ratios. So when autofluorescence ratios are very low, this spillover channel suddenly becomes the primary channel. Yeah, that was what we saw. And I can show you that essentially happens for any other dye, except the ones that have simple emission like Brilliant UV 395. Most of the dyes will have some kind of changes, and the changes will correlate with the changes in autofluorescence ratios. Now, something that we did was to do the experiment in the Aurora, but this time we tried to essentially match and do the same staining at the same time on the same day, having immunotrol and fresh human blood counted. So we knew the amount of lymphocytes that we have in the sample, and we were staining with the same ratio. Because we wanted to know what was the reason for the differences. And in addition to the idea of autofluorescence, we wanted to know things like, okay, are the fixed immunotrol cells have less CD4 epitopes available somehow? Have the fixation changed the number of CD4 molecules, so we're getting less stain index because of that? Or have the fluorochrome emission spectra have changed somehow by some kind of carrier fluorochrome interaction going on? And what we saw is that in the case of the Brilliant UV 661, if you look at the overlap of the CD4 positive population for immunotrol and fresh blood cells, they are perfectly overlapping. So this tells us that there is no difference in numbers of CD4. Actually, both samples are perfectly showing you the same levels of epitopes and everything. And what you see is an increase in the autofluorescence in immunotrol. And the autofluorescence is increasing in a way that in some cases will completely mask the resolution, the marginal resolution that Brilliant UV 661 will have in regions like the first few detectors in the Aurora. So you get an increase, you get a decrease in the dynamic range. Essentially, the whole signal compresses while the positives remain apparently constant. So this is the plot that I showed you before of the normalized stain index, but the one that is very interesting is this one here, in which I'm doing a different, essentially I'm subtracting immunotrol CD4 negative population medians and the fresh blood CD4 negative population medians. And I'm doing the same with the positive population. I want to know if the changes that I'm seeing in autofluorescence also reflecting changes in the CD4 population. Like essentially you're shifting the population up by a fraction. And when you do that, you see that they are actually matching. So in terms of logarithmic rendering, you don't see the difference because it's very small in terms of the scale of the logarithmic rendering, but there is an actual shift for both the negative and the positive in the same magnitude. And as I mentioned, one of the questions that we have is, are there any changes in spectra? There is no change in spectra. And this happens for all the fluorochromes. They are exactly the same fluorochromes. Now, when you think of the equation for brightness that we are using, which is this equation here, staining index could change due to two things, either because of the difference between the medians of the positive and negative had changed, or the standard deviation of the negative population have changed. And when you increase the median of the autofluorescence of the cells in immunotrope, together with the median, you are increasing the standard deviation. So essentially, you get a proportional increase in standard deviation of the variance of the measurement. So although the median look roughly the same, the difference between the medians of the CD4 positive and negative, the variance and the standard deviation of the negative have increased. And just by that fact, you will get a decrease in staining index. That's one way to look at it. The second way to look at it is a little more interesting, I think, because I use this equation a lot. The difference between the medians divided by the 2 times the radiation of the negative population. But sometimes when I want to know what is changing, I change the equation for this equation. By dividing the 2 terms by the median of the negative population, you get to equation that have the ratio between the medians of the positive and the negative, and the CV, or the coefficient of variation of the negative population. If you have, imagine, a sample that has a level of autofluorescence of 100, imagine, molecules, and you have 1,000 fluorescent molecules in the positive population, the ratio between these two values will be 10. Yeah. Imagine that now you add a constant number to both the positive and the negative. You would add 100. You will get now 1,000, 100, and 200 in autofluorescent unstable population. The ratio automatically goes to 5.5. And by adding essentially the fixed number to both the negative and the positive, you are gradually decreasing the resolution, which is something really counterintuitive, but essentially what's happening with the immunotrope and the fresh cells. So the autofluorescence is increasing in the same magnitude. It's also increasing the value of the positive population, but that increase, even if it's a constant increase, will lead to a decrease in resolution. And just to summarize this section here in terms of conclusion, because there are many ways you can read this. The first thing is that, well, the idea of brightness, the idea of brightness for the fluorochrome, typically when you think about it, it depends, of course, on the fluor properties and depends on the instrument sensitivity. But based on the data that I've just shown you here, it also depends on the autofluorescence, as much as it depends on the brightness of the dye and the instrument sensitivity. This means the following: that rankings that you have defined based on CD4 will not apply to older cells. So you might be thinking of a panel for myeloid cells. One of the cells have a higher autofluorescence in a specific region. Well, the relative stain index and brightness of dyes will essentially change based on the spectra properties of the cells that you're trying to measure. And this is a very simple example because it's applied to panel design, but imagine that you're trying to measure the same marker or the same fluorochrome across subsets that have different autofluorescence. Yeah. Following the same logic, your frequencies and your resolution of this DIN marker with a specific fluorochrome in each of the subsets will also be affected by the changes in autofluorescence between the subsets, which means that you can have a lot of contradictory results and results that will tell you, for instance, this population is negative when actually it's positive. It's just that it's too high intense of autofluorescence. So the only way to actually remove that effect and make the measurement somehow normalized is by doing autofluorescence extraction. So that's what I mentioned here by inconsistency in immunophenotype discovery project. So, and also in cases in which you are imagining producing major immunological events in which you are producing a massive inflammation, infection, cells will be evolving and changing in autofluorescence, and clearly measurement will be affected as well, because you're essentially comparing population on day 0 that have low autofluorescence, population on day 25 in which autofluorescence is very high. You will see a decrease in the marker, but actually it's not decreasing the autofluorescence have increased. So your measurements now are affected by autofluorescence, and you are getting to the wrong conclusions if you don't take autofluorescence into account. So that's what I mean here by signal resolution inversely correlates with autofluorescence of the carrier, because when we talk about brightness, we are talking about resolution in general as well. So CD4 clearly is not the best case in terms of dim signal, because it's not dim, but the resolution applies to both dim and CD4 in terms of the impact of autofluorescence. And the other one is this one, like the fluorescence spillover, the observed fluorescence spillover of dyes also depends on the carrier autofluorescence and the spectral signature. So when people say don't use as negative control cells of the same autofluorescence, well, part of the reason is this: you are not getting the same measure spillover if the cells have different autofluorescence, simply by the fact that the resolution in different channels will be changing. So to understand why autofluorescence is so important and to predict the impact that autofluorescence will have in things like measuring precision and resolution, I went back to papers that, for me, I think probably are one of the most important papers in cytometry. And they should get all these guys from Berman Coulter, James Hood, and Hoffman and Chase from Cytek. They should get like a mini cytometry prize Nobel for this, because what they did was to essentially provide the tools to mathematically understand the performance of instruments and predict the resolution of dyes and signals. And this essentially is what is under the CSNT methods and the QB short and things like that. Now, the theory is based on Steen. It was in 1992, even earlier paper, but the idea is essentially how can you define the factors that affect the spreading of the measurement precision in cytometry. And this is an equation that I call something like the general equation for CV, so spreading or precision. That is a function of the background, or B, the B in the theory of sensitivity is a function of background, fluorescent content, and quantum efficiency. And of course, it depends on other factors that are independent from Poisson or intensity, like for instance, intrinsic variation in the dye content or illumination inconsistencies. These are factors that would also affect the spreading of measurements, but they tend to only affect signals that are extremely bright. So any detector in cytometry, and this is the thing that people that study cytometry do not realize, is that their measurements have a scale of precision. And that scale of precision, you have areas of high precision for signals that are very bright. But as you go down into the edge of the signal towards the noise, you will start seeing this kind of spreading happening that have nothing to do with the spreading of the intrinsic fluorochrome or the marker. It had to do with the fact that you are getting into the region of Poisson counting, and you will get an error that will be essentially proportional, inversely proportional to the number of photons that you have. And essentially, you can see different scenarios depending on how intense the signal is. You can go essentially from general equation to this equation, which is essentially this constant here. It's a constant CV value. Now, but what about autofluorescence? When you look at the papers on sensitivity, the original papers, they don't mention autofluorescence explicitly. Like there is no mention of autofluorescence, and all calculations are based on the idea that autofluorescence is not there. So what is in the negative population is background, not autofluorescence. But when you do an overlay of rainbow beads, for instance, with different cells, including cell lines, granulocytes, monocytes, lymphocytes, you see that they have their own intrinsic fluorescence, of course, and you can go from lymphocytes and bacteria, and you see that each one of them will have a different intensity, and that intensity is real. It's real fluorescent, which means that the negative population is not negative, it's actually autofluorescent only. When you add autofluorescence as a source of photons contributing to the pulse that you get in cytometry, and you modify the equations that were originally defined by Wood and Hoffman and Chase, you get to this equation, which for me is a little more complete. You are taking now into account not only autofluorescent, but also autofluorescent. And you see that autofluorescent also, as fluorescent, will impact on the precision of the measurements. Essentially, it will work like a pair of fluorescent because they are both impacting on the signal pulse. And different populations, bacteria, viruses, and lymphocytes, and monocytes, and macrophages, specifically ambiola macrophages, will be essentially going down this ladder in which the intensity of the autofluorescence is so large that you become almost constant and independent of sensitivity factors. So this is what I mean by this evolution. So as intensity of autofluorescence increases, you start getting progressively a value that becomes constant. But it also means the following. When you're dealing with cells that have highly autofluorescent, sensitivity do not matter at all. Sensitivity essentially would not matter when you are handling cells of high autofluorescent. It would matter when you're measuring things like viruses, lymphocytes, and bacteria and DIN things, yeah? Which means the only way you can actually correct for the effect of autofluorescence is by removing it, yeah? Based on that equation as well, we go to another relationship, which is how to estimate the stain index of a fluorochrome based on baseline background of the detector, the quantum efficiency at that detector, and the value of autofluorescence the cells are essentially producing at that detector. And you see that it's an inverse correlation between stain index and autofluorescence. And in this case, autofluorescence is behaving like background. Essentially, they are negatively impacting on the stain index and the resolution of signals. And if you now imagine this equation, but for two different levels of autofluorescence, and you divide these equations, what you get is essentially this relationship that looks a little bit like a plot that I showed you earlier, in which you have an inverse correlation between autofluorescence and stain index ratio. And to demonstrate that this is true, we went to Aurora and to the 26 colors, the 26 fluorochromes that we have, and we calculated the stain index across the 64 Aurora 5L detectors. So for each CD4 antibody, we calculated the stain index across 64 detectors, at least 26 antibodies done in the process. And we essentially took the fresh stain indexes and selected values that were over 1 as a value of stain index somehow. It could be 1, it could be 2, it could be any value. And by selecting these detectors only for each fluorogram and CD4, we ended up with 720 data points. Now, these ratios of stain index between fixed and fresh cells, as you see here, were plotted against the ratio of autofluorescence between fixed and fresh blood cells. And you can see is that in the case of the violet, for instance, it's very clear there is an inverse correlation. So the ratio will increase as autofluorescent ratio decreases. It also happened in the blue. Not very clear in the far red regions in the UV path or the red detectors. And part of that is the fact that this equation not only depends on autofluorescence, but also background, the B of the quantum of the QMB theory. But there is a pretty good correlation overall. And you can see that the significance is massive. And there is an inverse correlation between these two values, which is essentially a demonstration of what the equations are telling us. Now, autofluorescence, in a way, I see it both as signal and background. So autofluorescence is a signal in a way that it depends on the sensitivity of the instrument. So the ability of resolve autofluorescence from baseline electronic noise or any other source of background at the edge of everything will depend on things like quantum efficiency and background. And you can see here an example of these samples that are CD4 and CD14 ungated leukocytes. And you can see in the Astreus, for instance, when you go from the Astreus to the LSR Forteza to the Cytoflex, there is a population here essentially being resolved from the lymphocytes in the Cytoflex, which are just suggested in the Forteza and barely visible in the Astreus. So sensitivity is important to see autofluorescence. But at the same time, autofluorescence behaves like background and behaves like background in the way that it reduces dynamic range and resolution. And the funny thing is that autofluorescence is not special in doing this. And although the equation that I've shown you is based on autofluorescence, there are many other things in cytometry that we normally are aware of that have the same impact as autofluorescence. So there is nothing unique about autofluorescence in doing this dynamic range reduction and stain index and resolution reduction. You can see the thing, for instance, if you are dealing with unblocked scatter that is triggered by the particles and hitting the detectors together with fluorescence. You will see that if you are using fixable live-dead dyes, you're increasing the value of the fluorescence in the cells that are unstained artificially by adding a dye. If you don't titrate this properly, resolutions compromise. You would do the same by fixing the cells. So immunotrol is a fixed example of cells that have been fixed And by fixation, essentially, you are reducing the resolution of your signals. If you're thinking of essentially taking panels from the unfixed state to the fixed state, well, you better be careful about the fixation and how strong the fixation is, because you can change your panel completely, including the detection of the markers by increasing autofluorescence artificially. The same will happen with structural dyes. It will happen with functional dyes. It happens with when you're doing titration. Essentially, you're not taking care of the antibody to cell ratio, and you put in too much, where you're increasing the background. Finally, something that is really provocative, but is actually true, is autofluorescence is no different than fluorescence spillover. Yeah, so fluorescence spillover is doing exactly the same. It's adding fluorochromes, it's adding photons to the measurement in another channel in which you want to measure another fluorochrome. The same effect will happen. And as with fluorescence, in which you have to do a compensation and a mixing, well, with autofluorescence, you should do the same if you want to recover the resolution somehow. Now, before I was showing you data based on raw measurements, I wanted to also know, and this is something triggered by a question in the last seminar, what happened when you do a mixing? A mixing, does a mixing increases the resolution of dyes? Does a mixing decreases the resolution of dyes? How a mixing compared to raw data resolution, and how this compares to a mixing plus autofluorescence extraction. And this is the results that I'm showing you here. So for the fresh samples, for fresh lymphocytes, there is not much of a difference between raw values, which are these intermittent lines, between raw values, 10 index, and what you get after a mixing. Yeah, the difference is not really much. It's not significant. And I have seen in some cases that it could be even worse by a mixing. Well, sorry. No, this, the autofluorescence extraction. So you get essentially similar value between raw and a mix. And when you do autofluorescence extraction of fresh lymphocytes, you get a marginal increase. And as I'm saying, as I mentioned, I've seen before that it doesn't increase at all. It actually is similar or lower. So if you're trying to test autofluorescence extraction algorithm with fresh lymphocytes, you will never see any effect, and you will think that autofluorescence extraction is not important. But if you're applying autofluorescence extraction and a mixing to fixed samples, like in the case of immunotrol, we essentially saw something really surprising, which is the unmixing makes the resolution worse. by the simple fact of unmixing, this is a mixing of one color. So essentially, we're not mixing one color at a time. We are not doing a panel. We are doing one color and mixed against the immunotrol autofluorescence. And the unmixing produces worse results than raw in many cases, and it's significant, very significant. And when you do autofluorescence extraction, you get to values that are similar to raw or better, and better specifically in regions in which autofluorescence is really high, when you have the peak maximum of the immunotrol sample unstained. Yeah. So yeah, you get sometimes improvements, sometimes it's not much of an improvement. It's overall at the level of raw or better. Now, we wanted to investigate essentially this example here, the example of the mixing creating worse results than raw. And in order to do this, we changed software. Instead of using SpectroFlow, we use FCS Express, and we got the same effects in FCS Express. So when you look at raw data and you look at the mixed PE data and they're mixed with autofluorescence extraction, of course, here you will get an increase in a way compared to a mix only, because you're removing the autofluorescence, but also you are increasing the spreading somehow. In the case of a mix only, something really curious happened, which I cannot explain, is that you get a shift in the whole population up. So essentially negative and positive shift by magnitude that is close to 10,000, which is what I'm showing here. So I don't know essentially what happened, but it happens with FCS Express and SpectroFlow. And that increase, that proportional increase, as I showed you before, leads to essentially the same decrease in resolution. And it's a massive change. Yeah, you go for 231 in the raw data to 67 in the unmixed, and 165 unmixed with autofluorescence extraction. But essentially, with mixing with autofluorescence extraction, you recover part of the resolution compromise, but you never get, in this case, at the level of raw. So it's not a perfect system. That's what I mean. It's not a perfect algorithm.
We have a couple more minutes before we have to move on, if that's okay.
Yeah, it's okay. It's okay. No, it's okay. I will finish very soon.
All right, fantastic.
Yeah, so in summary, just to show you essentially all the things that happen with autofluorescent extraction, is that autofluorescent extraction is a balance. You have a balance between two effects. One is a positive effect in which you have a decrease in the median of the negative and increase in dynamic range. But also you have the error that you generate after autofluorescent extraction, which is similar to the error that you get imaging after compensation. You are removing a population, a median, and taking it somewhere down to a value that is lower, but you're somehow carrying a variance that comes from the negative population in the former states. And you can see this here. Now, surprisingly for me, the standard deviation of the fixed and the fresh after autofluorescent extraction reduces a little bit. So if you measure actual variance, the mixing is reducing the variance in a way. But that decrease in the variance, which is not really massive compared to the increase in the decrease in the median that you get, takes you into the case in which you have a maximum values of CVs. So the CVs would increase, and the increase is significant for the negative population in both fresh and fixed cells. So a mixing with autofluorescent extraction increases the dynamic range, but at the same time increases spreading around the negatives. And this is one of the last slides. I wanted to know when you should apply autofluorescent extraction. Imagine if you're running a sample that you don't have any reference for it. How do you know what level of autofluorescence that cell have? If you're talking about a cell line or specific cell that is pure, you don't have any kind of internal reference, how do you know? So what I did was I took all the negative populations for CD4 in the fixed and the fresh samples in Aurora after unmixing, and I calculated the values of MFI and CV for all the negative CD4, yeah? And I also compared that to the positive CD4, and you can see something really interesting is that there is an inverse correlation between coefficient of variation and the intensity measured by the MFI in the Aurora. And when you go to populations that are CD4 positive, the CVs are constant. When you go to populations that are really low in intensity, they also tend to have the larger CVs. And you can use either MFI or CV as an indicator when you're talking about lymphocytes of a relative predictor of improvement. So in the case of MFI, if you have a population that have around 10 to the 4 after unmixing in the Aurora, if you apply autofluorescent extraction, your resolution should improve somehow like 4 times. If your cells are around between 10 to the 2 and 10 to the 3 after unmixing, you will not get any improvement with autofluorescent extraction. Yeah. And if you're doing the same with instruments that are not Aurora, and you want to know what is the relative intensity of your sample, something that I would do, I would run the cells together with Rainbow and use the Rainbow as some sort of intensity ruler to know how bright my signals actually are. Because if you're dealing with a single population, you never know. You can put the population anywhere based on gains, but the autofluorescence will still be there affecting your resolution anyway. So I think I will finish here. The remaining of the talk was essentially repeating the same concepts in the case of the immunophenotype discovery panel with the tomato. But I think if you go and look at the lecture that I did on March, you will get most of the ideas the same. But essentially what I do in this section is showing how important is autofluorescent extraction to be able to see the tomato reporter in populations like alveolar macrophages that are extremely autofluorescent and across all detectors. And without autofluorescent extraction, you might not be able to see that there is a phenotype at all. So I think I will finish here. Thank you so much.
Oh, thank you. It's a really fascinating talk. I really personally enjoyed it. In the interest of time, I'm going to save, there's a lot of questions and a lot of good conversation. So in the interest of time, I'm going to save that until the panel discussion, and I want to remind our